4 and chapter 6 this week. Alright, so if you're using the textbooks, remember the textbook is the online textbook that I gave you last semester. Ryan isn't here today, so so you'll have the textbook right there. But you'll just share it with Ryan in case he doesn't have it. Anyway, so just let you all know that the textbook we're in chapter 4 and chapter 6. So if you look at the course outline has the chapters that we're doing. Alright, so just check the course outline, it tells you what chapters. And for those of you all that may feel like in class you're still a little confused, I would recommend just, if you have time, right, read through the chapter. Right, read through. The chapter probably explains it better than my voice. Alright? So I just let you know straight up. Alright? Alright. So substation. Alright. I was late that night because substitution. I literally need to change that right now because it's going to cause a crap on me. Alright. Alright, radical substitution. So, we are starting reactions, folks. Alright, we have our test next week. Monday, the test will be on everything covered up to week 5. So not week 6. So all of this that we're going over this week will not be on the test. Alright? I will post another quiz, and I think the assignment that I post will not be due until after the test. Okay? So the assignment that I'm going to post is for this stuff, not for the test. So if you did the assignment, that's what's coming sort of on the test, and then the quizzes, this quiz that we just took, and then the quiz this week that I'll put on a sheet. Alright, so let me write that down so you know, because I feel like when I write stuff down, so quiz 3, I believe, is going to be on Achieve, right? And that will probably be due like Friday night. So that way it gives you all time to review the answers in time for Monday, right? So that's quiz 3. Then assignment. I've given you all 2 assignments, I think, already, or how many assignments have I given you already? 2, right? So assignment 3 is not due for like a week and a half. Alright? But that will be posted this week, and then you'll do it after. And then test number 1 is next Monday. Right? And that's based on lecture slides 1 through 5. Right? Everybody alright? I like to be clear. Alright, so this is week 6, and these are our objectives. So, with our, what we're going to do is radical substitution. We're going to talk about the mechanism for how we do radical substitution. We're also going to talk about what is homolytic and heterolytic fission. We'll talk about the stability of the different radicals. And then on Wednesday, we'll get a little bit complicated, right? We're going to talk about kinetics and thermodynamics of reactions. We're going to bring some math, a little bit of math, but mainly just to kind of help us understand how kinetics change based on the stability of our radicals. So we'll talk about on Wednesday kinetics and thermodynamics, and then next week we'll begin SN1, SN2, E1, E2. So for those of you all that took the class last semester, the topic we're going to cover next week is completely new. Alright, so we're going to start a completely new topic that will be included because you all are doing SN1, SN2, and E1, E2, right? So I want to give them a foundation this semester. we've done naming already in Intro to Organic and last semester. So to name a haloalkane, we simply choose the longest carbon chain, like we remember. Even if the halogen is not bonded to any of those carbons, you still use the longest carbon chain. And you're always trying to assign the lowest possible numbers for positions. You all shouldn't have to write this down because this should be like, you all know this already, right? This is review. But if you don't want to write it down, I'm going to do this stuff. Right? So we're looking for longest carbon chain and we're looking for lowest possible numbers, right? So if I have this example here where I have 4 carbons, right? I'm going to number it from left to right or right to left. How will I number this? Left to right or right to left? Left to right, right? So carbon 1 will be on my left, carbon 2 will be chlorine, carbon 3 and 4. Right? So I number it 1, 2, 3, 4. So my chlorine is on carbon 2. Right? So carbon 2 is my chlorine. Right? This is like a sidetrack tangent. But Joseph, does the mic pick up a bit on that? It's clear? Alright, so anyways, sorry, I was on tangent. Alright, so carbon 2, we have the chlorine. So how will we name this haloalkane? 2-chloro butane. Right, 2-chloro butane. Alright, so 2-chloro butane, like I said, is review. Let's do one more. Alright, so I have this long chain. Alright, do I start naming left to right or right to left? Or does it matter? It's in the middle, so it doesn't matter which side. So just for aesthetics, we'll number from left to right. So 1 through 7. Alright, and on carbon 4, that group is a little bit more tricky to name. So the fluorine is on the ethyl group on carbon 4. Right? So to name that one, we have to also number the carbon, the ethyl group on the end. Alright? So we'll number the ethyl group on the end. So what we're going to do is to name this one, the ethyl group that's attached as a side chain, we're going to put into brackets. Alright? So we put into parentheses. And the naming of it, we'll go ahead and put it. So on carbon 4, so before what would we name this just as itself, by itself? What would we name that? Just this part. What carbon is this chlorine on? Carbon 2. So we have to use this as carbon 2. Because carbon 1 is the one that's attached to the main chain. So carbon 2, so it will be 2-fluoroethyl. Right? So 2-fluoroethyl is this group, and it's attached to carbon 4. So what we do is, we put it as carbon 4 has a 2-fluoroethyl group on the heptane chain. So that's how you name, if you have a fluorine on a side chain, you name the side chain in brackets. Parentheses, parentheses, and you label what carbon that parentheses side chain is. Right, so 2-fluoro. Alright, we also have a little bit more examples, but I'm going to run through these again. So again, we're trying to do lowest numbers. So for this one, we're going to go left to right or right to left. Left to right, right? That's the lowest number in. So we go from 1 through 9. So how would we name this straight chain alkane? So what is the group on carbon 2? What group is that on carbon 2? Methyl. And what group is that on carbon 6? Bromo. Which one do we write first? Bromo. So it's 6 bromo, 2 methyl, nonane. Alright, nonane is the end of it. So 6 bromo, 2 methyl, nonane. Alright? So now, the last one that we'll do as an example is when it's in a ring, numbering is based on alphabetical order. So I have two halogens here, bromine and fluorine. So because we're naming it on alphabetical order, I'm going to name it I'm going to number it based on which one, bromo or fluoro? Bromo. So bromo becomes carbon 1, fluoro becomes carbon 2. Alright? Now, 3, my bad. Now because both the bromine and the fluorine are coming towards us, we have to use stereochemistry. So what will we name this? Cis or trans? Cis. Right? The hydrogens are both on the same side. So the hydrogens are both facing away from us. So this is cis, and then how do we name from there? So it's cis, 1 bromo, 3 fluoro, cyclohexene. So cis, 1 bromo, 3 fluoro, cyclohexene. So these are just different examples of how we name haloalkanes. Like I said, this is review. I recommend going back through it, but you'll already know those rules. Right? So these are just some common substituent alkyl groups that you'll find. So this is an isobutyl bromide. This one is a sec-butyl bromide, and this is the terbutyl bromide. And again, it's just based on when we have these are like 3 different isobutyl groups. So this is sec-butyl, isobutyl, terbutyl. Alright? And when the bromine is sort of on the end of these, we sort of name them differently. Alright, so that's how we have those groups, right? So look at it that way and alright. So again, these are just common names. I won't really have you do those too much. Some other common names. If I have a halogen on just 1 carbon, it's a methylene. They're also like a halo form, carbon tetrahedride. Again, those are not common. This is what I want you all to remember. If I ever use methylene chloride, right? So methylene chloride is a solvent that we use. This is because this has sort of, it's the other word for methylene chloride is dichloromethane. Hold on, excuse me. So another way to name methylene chloride is also dichloromethane or DCM. So it's a very, very common solvent we use in organic chemistry, so that's why we name those. Another one that you all probably heard of is chloroform. Right? Chloroform is, you see in movies, not people are looking at one. But it's also a very, very common solvent. It's actually a common solvent that is used for proton NMR. So if I want to dissolve a substance and I want to take its NMR structure, so NMR is just like a structure of all the atoms and how it's bonded, I usually use chloroform in that as a solvent because it dissolves a lot of stuff, right? A lot of organic molecules. Alright? And then another one is carbon tetrachloride. So these are just common halogenated solvents. DCM is used a lot, chloroform is used a lot. I haven't used carbon tetrachloride. I'm not sure how many people actually use it, but I do know chloroform and DCM are very much widely used, right? And they're very, what do you call it? When they evaporate quickly, what's that called? Volatile. They're very volatile. So they evaporate a lot. We also talk about primary, secondary, tertiary. That's just based on how many carbons are attached to the halogen that's attached to the carbon. I said that wrong. If the carbon that the halogen is attached to, right? So let's look at these three carbons. So the carbon that this halogen is attached to, the carbon that this halogen is attached to, and the carbon that this halogen is attached to, tells us whether we have a primary, secondary, or tertiary alkyl halide, right? So for example, this one, what kind of alkyl halide is this? Primary, secondary, tertiary. Primary, because the carbon that's attached to this bromine only has one carbon attached to it, right? What about this one? Secondary, all right? And what about secondary? And the last one is tertiary. So this is super important because it's going to determine our reactivity. So when you talk about substitution of alkyl halides, the reactivity of those alkyl halides are based on if you have a primary, secondary, tertiary alkyl halide. Alright, so just remember how to identify those. The easiest way is look at the carbon that's attached to bromine and look how many hydrogens it has. So if it has two hydrogens, it's a primary. If it only has one hydrogen, secondary. And if it has no hydrogens, tertiary. That's the easiest way to identify, right? But also you can just say how many carbons. Again, all this review. So uses for alkyl halides, because I like to know why I even studied this. That's why I like chemistry. It has real world applications. We use a lot of alkyl halides in industrial and household cleaners. Like I said, chloromethane and DCM are also very common solvents. Alright? They also use in anesthetics. When they put you to sleep, chloroform is used as a general anesthetic, but it is toxic and carcinogenic. Now they don't use chloroform as much anymore, right? But you have to be careful. So now they mix it in something called halothane, which is a little less toxic, right? And you'll see a common theme with alkyl halides is that a lot of the uses are very toxic, right? So we try not to get our halogen alkenes because they're very. The reason it's toxic is because the halogen could be substituted easily and react with your body. So another use is freons. And this is just to give us context for why we study halogen alkenes. So these are some of the areas we see it is in freons, which are like refrigerants, foaming agents. Right? They also cause harm to the ozone layer. So remember, like CFCs. I don't remember that was a big thing. CFCs, like when we did in a canister, and you. All right. So like when I was in like high school, there was this huge thing about the ozone layer. Oh my goodness, we're causing holes in the ozone layer because of these CFCs, right? So what CFCs were? They were chlorofluorocarbons, and those carbons were used in propellants. So anything that could spray, any spray cans for like your fish or your like Baygon or whatever, would have these chlorofluorocarbons because it would help take something from a liquid to a gas real quick. So that was in a lot of our spray cans, and because people were using it all the time for a lot of different things, it's not just Lysol spray, whatever, they said that those CFCs were causing damage to our ozone layer and causing holes in the ozone layer, and they banned the CFCs. So now, because you all have different generations, you all even know what a CFC is, because it's like this already been banned. Because they realized how toxic, how bad it was for an environment. So they found other options. And that's where we got the change it up, right? And then the last, sort of most important, is in pesticides. And they help keep, like I said, notice the common theme: toxic, toxic, toxic. So when we work with halogen alkanes in a lab, you usually have to work with it in a hood. Alright? You don't want to sort of inhale all of it because they are toxic. Now, chloroform and DCM, yes, they're toxic, but you need to really do a lot of it. Like we used to use it as anesthetic, so it's not as bad, but it can be, right? But anyways, the rest of them are really toxic. So you use a lot of halogen alkanes and pesticides, and they sort of cannot be broken down by the bacteria. So if you put it in there, it kind of kills your insects, right? But not as toxic to us animals. Alright, so now let's talk about preparation of these alkyl halides. So this is from chapter 4, so now we're going to go back to chapter 4 and look at the different reactions that we have with halogen alkanes. So we have chlorination. We'll talk about how to make the halogen alkanes from an alkane, and also bromination. And then there's one other version, but we're not going to talk about it too much, but this is the free radical allylic halogenation. So this is when we have an allyl group, and we'll talk about what allyl groups are, but they're basically like alkenes that are next to another carbon that's a symbol. Right? But focusing this week is on this part. So our focus this week is on this part. Alright, so let's look at the general reaction. And this is where you're also going to start to have to write down and memorize. But the general reaction for using chlorine to halogenate an alkane is two methods. We can use heat or light. Alright? So if you use chlorine gas, so Cl2, and you have a methane and you use heat or light, you can get I can't even change it. So you all see the chloromethane has a hydrogen instead of a carbon. I'm sorry that it messed up. Right? Okay, forget it. Alright, much better. Alright, so we can take the carbon and substitute a chlorine on the carbon, and that gives us the methylene chloride. And then you have a byproduct, which is hydrochloric acid, right? So the two mechanisms for us to chlorinate any alkane is using heat or light. The requirement of heat or light is sort of to start the initiation step of our halogenation, and we'll talk about all those steps. But the most effective wavelength is the blue wavelength. You don't have to memorize this, but just so that you're aware that if you have the blue wavelength, so almost like a UV light, usually is the best way to sort of start these reactions. So usually UV light is the light that we use to start this reaction, and it's easily absorbed by the chlorine gas. And many products formed by the light causes like this chain reaction. That chain reaction. Alright, so now let's talk about the steps to halogenation. So if you all remember, does anybody remember what are the 3 steps of a radical? Forming of a radical substitution. One of them is already named there. Initiation. Alright, so that's step 1 is initiation. So we have to create the radical, so that's initiation. Remember the second one? Propagation, right? So propagation is where now we go ahead and add to the chain, and then the last one, termination. Alright, so we're going to review those 3 steps: initiation, propagation, and termination. Right? So first, let's talk about initiation of the radical. So we have to initiate the system, create a radical then starts a chain reaction. This is why, ladies and gentlemen, alkyl halides can be so dangerous, is that if you initiate a radical, radicals are very reactive, and if it's initiated in our bodies, that's what causes a lot of cancer, right? These free radicals. So it's important for us to be safe, right? So initiation is our first step to generate the radical intermediate. The second phase is propagation, and the definition really is just to take the radical intermediate, all right, and with a stable molecule to produce another radical. So you take one radical, so you make the radical, you take a stable molecule, by attacking it, it creates another radical. That radical then attacks another stable molecule, and it keeps going and going until our last step, which is termination. Right? So just so that we understand the general mechanism. I have a stable molecule. I use heat or light to create a radical. Right? That radical then reacts with another stable molecule to create another radical. And that keeps going until the end, where we terminate to form two stable molecules. Well, not two, one stable molecule. Two radicals, right? So this will be two radicals will join together to form one stable molecule. So stable molecule, this is the initiation. This is the propagation. Alright, and then this is the termination. So those are our three different steps that we have for radicals. So that's a general mechanism, right? Now we're going to go into how do we draw these and exactly how do we make these radical intermediates, right? And that's it. So let's look at the beginning. So what is forming your radical is a homolytic, so remember that term, homolytic cleavage of the chlorine bonds. Right? So chlorine is making a bond with itself, and when you add light, it splits it in half evenly. And that even split is what creates a radical. Because remember, a bond is made up of two electrons, right? When I do a homolytic cleavage, meaning an even split cleavage, what that does is it creates two radicals as the intermediate. So by splitting it down the middle, one electron creates an uneven pair. So it's not a pair of electrons anymore. It's not a lone pair. It's an actual radical because it's missing an electron. Now, how many electrons want to have pairs, right? They want to work in pairs. So because it's just one electron, this is going to want to attack something else, right? So it could be methane or whatever, right? So that's why this is so reactive, is that once you split it evenly, you create these very reactive radicals, right? So that's the initiation, the formation of the chlorine atom. So it's called a free radical. Now the propagation step. So this same chlorine atom that is now a free radical is now going to react with a methane. So if you see, and remember, we have two types of arrows. We have half arrow full arrows. Alright? Half arrow represents single electron. Full arrow represents electron pair. Alright? So if I draw if you see a half arrow, that means you're making a single electron. Alright? So you have a single electron, making that single electron with the hydrogen. That hydrogen is going to form a bond, forming the H bond. Now look what happens then.